Hello everyone, welcome to M Math Academy. Today in this video we are going to explain the topic functions, and within this chapter we are going to explain the special types of functions. So in this chapter we are going to explain linear function, constant function, quadratic function, identity function, modulus function, composite function, rational function, inverse function, and some other functions as miscellaneous. So linear function. Linear function is a function of the form fx equal to ax plus b, where a and b are real constants. A, b belongs to R, real number R. The graph of a linear function is always a straight line. In other words, a linear function is one whose graph is a straight line. A linear function has one independent variable x and one dependent variable y. Graph of linear function fx equal to 3x plus 2. This is an example. This is the graph. So of this linear function fx equal to 3x plus 2, this is the graph, which is a straight line passing through these points, and this is a linear function. The graph is a straight line. Constant function. Constant function is a function of the form fx equal to b, where b is a constant. The graph of a constant function is horizontal line with y-intercept b. No matter what value of x we choose, the value of the function always remains the same, as the b value is always a constant number. A constant function is a special type of linear function whose slope is 0. Graph of constant function fx equal to 2. This is the graph of this function fx equal to 2, and we can see, since b equal to 2 is constant, the graph of the function is a horizontal line passing through y equal to 2. Quadratic function. Quadratic function is a function of the form fx equal to ax square plus bx plus c, where a, b and c are real constants. A, b, c belongs to real numbers r and a not equal to 0. A quadratic polynomial function is a second degree polynomial. The graph of a quadratic function is parabolic. Parabolas may open upward or downward and vary in width and or steepness based upon the quadratic polynomial, but one thing in common, they all have same basic U-shape. Example, graph of function fx equal to x square plus 2x minus 1. So this is the graph, which is a parabola, and this parabola is opening upward. Now identity function. This is a function of the form fx equal to x, where x value is the same as the y value. The graph of an identity function is a diagonal passing through the origin 0, 0. An identity function always returns the same value that is used as its argument. That is, for f being identity, the equality fx equal to x holds for all x. This is the graph of the identity function fx equal to x passing through the origin 0, 0. Now modulus function or absolute value function. Modulus function or absolute value function is a function of the form fx equal to mod x, where x is a real number. In mathematics, modulus or absolute value of a real number x, denoted by mod x, is an algebraic expression within modulus symbols indicating the non-negative value of x without considering its sign. The modulus function is defined as fx equal to mod x, which is equal to x if x greater than or equal to 0, which is equal to minus x if x less than or equal to 0. So this is the graph of the modulus function fx equal to mod x. The graph of an absolute value function has a V shape. So fx equal to mod x, the graph of this function is always a V shape like this. Since the graph is in two pieces, it is a piecewise function. Composite function. A composite function is created by substituting one function into another. A composite function of f and g is this, which is read as f composed with g or f following g, f composed with g. So this is the symbolic representation. F composed with G equal to this, or it can be expressed in this form: F composite Gx equal to F Gx, or in this pattern it can be expressed as well. If we recap, this type of symbol we have already mentioned in our previous videos. This is read as f is the function which converts x into fx. Now if f is the function of x which converts x into fx, and g is the function of x which converts x into gx, the composite function of f and g will convert x into fgx. Note: f composite gx not equal to z composite fx. The notation f composite g is read as f composed with g, or f following g, or f of g, f on g, f after g, f circle g, f round g, f about g, f then g, etc. These are just different names or different types of names, but we usually read this as f composed with g. This is the most common name. Composite function example. So there are two functions here. Find the following. These are the questions. This is very straightforward. This is a function and this is another function. Then if we want to find the composite function, we just substitute. First of all, we have seen in the previous page that f composite gx can be written as fgx. Then basically we are substituting this gx function, which is 3 minus x here. Then we are trying to find the function f substituting x by 3 minus x. So in this function we are substituting 3 minus x, then simplification. This is the other way, g composite fx. So in this case we can initially write down g composite fx equal to g of fx. Then g is unchanged here, but function of x we are writing down. Then basically we are substituting x in the function g by 2x minus 2. So g 2x minus 2 we are finding from here. 3 minus gx, function of g is equal to 3 minus x. So basically we are substituting x by 2x minus 2, then simplification. This is another question and this is another part. Next, composite function. There is a worksheet here. You can try to solve this. Next is rational function. Rational function is a function that can be expressed as the ratio of two polynomials where the denominator is not equal to 0. Any function of one variable x is called a rational function if and only if it can be written in the form this: fx equal to px over qx, where px and qx are polynomial functions of x and denominator qx not equal to 0. Domain of a rational function fx equal to px over qx is the set of all values of x for which the denominator qx is not 0. General form y equal to ax plus b over cx plus d, where c not equal to 0. Rational functions are characterized by asymptotes, which are lines the function gets closer and closer to but never reaches. There is an example here. The parent function of a rational function is fx equal to 1 over x, which is the simplest example of a reciprocal function. The graph of this function is a rectangular hyperbola. Now this is the graph of the rational function fx equal to 1 over x. There are some observations from this graph here. The graph of this rational function has two pieces in the first and third quadrants. One piece here in the first quadrant and one piece here in the third quadrant. Fx equal to 1 over x is undefined when x equal to 0. At x equal to 0, the graph is undefined. That's why the graphs are not reaching at this point. Now next point is, if x tends to plus minus infinity, fx tends to 0. If x tends to 0 right or left, fx tends to positive or negative infinity. The asymptotes are the x-axis and the y-axis. As x approaches 0, the graph starts getting very large on both sides of y-axis. This is called the vertical asymptote. So vertical asymptote is y-axis, which is this x equal to 0. The y-axis is the vertical asymptote. Similarly, um, when x gets very large, both positive and negative, the graph approaches on both sides of x-axis, y equal to 0. This line is called horizontal asymptote. So x-axis or y equal to 0 is the horizontal asymptote, and y-axis or x equal to 0 is the vertical asymptote in this particular function. Rational function, there is an example here. General form of rational function is y equal to x plus b over cx plus d, c not equal to 0. There is an example here, fx equal to 3x plus 6 over x minus 1. So solution step by step. We find the graph first, and we find y-intercept x equal to, by substituting x equal to 0, we find y equal to minus 6. So 0 minus 6 is the y-intercept of this graph. Similarly, in order to find the x-intercept, we substitute y equal to 0 in this graph, and we can find x equal to minus 2. So minus 2, 0 is the x-intercept of this graph. Then we can draw the graph, and we can see vertical asymptote x equal to 1, and the horizontal asymptote we can find y equal to 3. So y x equal to 1 is the vertical asymptote, this dotted line, yellow line, and y equal to 4 is the horizontal asymptote. Then we can find some points. Since the y-intercept and x-intercept are already in the left region, x less than 1, we won't need to get any points there. We need to find a point in the right region, x greater than 1, which is, we can substitute x by 2. So f2 we can see 2, for f2 we can find at x equal to 2 we can find y equal to 12. So 2 and 12 is another point, and that's how we can find a point like this. Rational function example, this. So we find y-intercept, then x-intercept, then we can find draw the graph, then vertical asymptote x equal to 2 and horizontal asymptote y equal to 4. Now inverse functions. An inverse function or anti-function is defined as a function that simply reverses or undoes the action of another function. That is, if fx turns a into b, then f inverse x must turn b into a, which is very important. So fx turns a into b, then definitely the inverse function of this fx, which is f inverse x, must turn b into a again. So for a function fx, its inverse function f inverse x is defined by f composite f inverse x equal to f inverse composite fx equal to x. So both of these result gives us x. F composite f inverse x gives us x. Similarly, f inverse composite f gives us x as well. Alternative definition: if two functions fx and gx are such that composite f composite g equal to x and g composite f equal to x, then we can conclude fx and gx are inverse functions to each other. So fx equal to g inverse x and gx equal to f inverse x. Note, f inverse x we are mentioning many times. Remember, f inverse x is not any negative exponent or the reciprocal of fx. So f inverse x is not equal to 1 upon fx. This is not the case. In inverse function, the f inverse x is indicating the inverse function of fx, not the reciprocal of fx. Inverse functions mapping. So from mapping perspective, we can explain the inverse function as well. Example of mapping of a function fx and its inverse function f inverse x. So this is a mapping of function f. Suppose a1 to b, 2 to a, 3 to c, 4 to e, 5 to d. Then f inverse must have to be like this. That's just opposite. This a b c d e comes to this side, and 1 2 3 4 5 comes to that side. And remember, 1 was connected with b, here also b connected with 1, 2 connected with a is with 2. This is written here f. So f maps 1 to b, 1 to b, 2 to a, 3 to c, 4 to e, and 5 to d. Now we can see f inverse maps the exactly the opposite. 1 to, it was 1 to b in f inverse it becomes b to a. So b to a, it was 2 to a in f, in function f, 2 to a, it becomes a to 2 in this case, a to 2, and likewise. Note, the domain of f inverse is equal to the range of f. So we know in mapping this is the domain and this is the range. So the domain of f inverse, in case of f inverse, the domain becomes the range of f. This was the range, it becomes the domain here, and vice versa. The range of f inverse is equal to the domain of f. If a b lies on function f, then b a lies on its inverse function f inverse. A function fx and its inverse function f inverse x are reflected over the line y equal to x. This line passes through the origin and has a slope of 1. A function y equal to fx may or may not have an inverse function. Some functions have no inverse function, as a function cannot have multiple outputs. Inverse function example. Find inverse function of fx equal to negative 1 over 3x plus 1 by variable interchange. Solution. So first step is substitute y for fx here. So instead of fx we are writing down y equal to negative, same function here, just we are substituting fx by y. Second step, switch x and y in this relation. So x equal to negative 1 over 3 y plus 1. Step 3, solve for y from this step. So we are just solving this for y, we find this. Then last step is inverse function f inverse x equal to negative 3x plus 1. So this is the inverse function of this function. Another example. So this is the function. There are a few questions. Sketch function fx and f inverse x on the same graph. Then find f inverse x using coordinate geometry as well as variable interchange. Prove this relation. Solution. So this is the function fx. We can see function fx equal to 3x plus 2 passes through 0, 2 and 2, 8. So f inverse x passes through 2, 0 and 8, 2. So whenever we see fx, this function passes through 0, 2 and 2, 8, we can conclude f inverse x, which is the inverse function of the original function, passes through 2, 0 and 8, 2. It was 0, 2 and 2, 8, so it becomes 2, 0 and 8, 2 in case of inverse function. Now gradient of y equal to f inverse x is 2 minus 0 over 8 minus 2. So 2 minus 0 by 8 minus 2 equal to 1 over 3. So equation equal to, we can find the equation of this, which is y equal to x minus 2 over 3, f inverse x equal to x minus y over 2. So this is by coordinate geometry we are finding the equation of the f inverse function f inverse x. Similarly here by variable interchange, as we have seen in the previous page, by variable interchange we are trying to find the inverse function now. So y equal to 3x plus 2, we switch x and y, then we solve for y, and that is the inverse function here. So this is the graph of this example. So original function was 3x plus 2, which was here y equal to fx, and we find the inverse function like this, and this is y equal to x is here, the asymptote. So if sorry, this is not asymptote in this case, inverse function. So this is the mirror, we can say y equal to x. So this y equal to fx and y equal to f inverse x, they are in both sides of this line y equal to x, and just by these points 0 2 and 2 8, the original function is passing through these 2 points 0 2 and 2 8. This is the graph of the function, that's how we are drawing. And the other function is 2 0, f inverse x is going through 2 0 and 8 2. So 2 0 is here and 8 2 here, and then finally we have a last part, we have to prove this. This is very straightforward, and we can prove this. So that's pretty much. Now we have the last part. We are just trying to mention a few more functions, miscellaneous. So reciprocal function. A reciprocal function is a function of the form fx equal to k over x, where k not equal to 0. The simplest example of a reciprocal function is fx equal to 1 over x, which means k equal to 1. So fx equal to 1 over x is the simplest reciprocal function. Next is identity function. The function y equal to x is the identity function, defined as this. This is the identity function. Next is self-inverse function. Any function which has an inverse and whose graph is symmetrical about the line y equal to x is a self-inverse function. A reciprocal function fx equal to 1 over x, x not equal to 0, is said to be a self-inverse function if fx equal to f inverse x. Algebraic function. A function defined by an algebraic expression is called an algebraic function. Example, fx equal to x square plus 2x minus 1. Trigonometric function. A function of the form fx equal to sin x or fx equal to cos x, etc. is called a trigonometric function. Exponential function. A function in which the variable appears as an exponent is called an exponential function. For example, fx equal to a to the power x. Logarithmic function. A function in which the variable appears as an argument of a logarithm is called a logarithmic function. For example, fx equal to log x to the base a. So this is all about this chapter. Thank you for watching this video. Please like, share and comment, and don't forget to subscribe this video.